So today we're going to talk about one of my favorite, if not my favorite, idea of the school year. So, which is mathematical induction. So, before we actually start using mathematical induction, let's first talk about what mathematical induction is all about. So, when you hear the words mathematical induction, we're basically using mathematical induction as a method of proving mathematical statements true. So in other words, this is a method used to prove certain things in mathematics, which is kind of like a tool that could be used in various methods. So you'll see that the principle of mathematical induction will show up from time to time in proving certain things. So sometimes you notice, hey, this is a better approach. Mathematical induction is a better approach to use to prove something is true. So to use the idea of mathematical induction, there's actually 3 steps. So there are 3 steps involved in proving using the principle of mathematical induction. Okay, so the first step, which is to kind of get the ball rolling, and I'll kind of explain to you guys why these steps are the way they are. So we're going to show that the case n equals 1 is true. So when we say the case n equals 1, this is pretty much our first case, right? So whatever statement we're making, we need to show that it's true for the first case. Okay, so this is just a simple plugging in whatever our first value, our domain value is, to check it and make sure that works. And then the second step is basically kind of like a statement step. So this is assume that the case n equals k is true. Okay, so, and I'll talk about why this assumption is important in a minute. And we can make this assumption, and I'll talk about why we can make that assumption. But here comes the difficult step, or the important step, which kind of brings everything together. So I'm going to put an asterisk here, just to kind of show emphasis on this step. So the second step is an assumption. It's a statement we're making, we're accepting it, and we're moving on. The third step is we need to show that the case n equals k plus 1 is true. So what are we doing here? We're showing the case after the kth one, right? If this is k, this is k plus 1. So we want to show that the k plus 1, which is 1 after k, this also is true for the statement provided. And once we do that, so once these steps are used and they're all validated, so we would say that these steps will show that the specific statement is true for all cases. Which completes the proof. Okay, so let's kind of go back to why this completes the proof. See, what's important is we're saying, hey, look, suppose that n equals k is true, right? This statement that we're saying is true for the kth case. And when we show the one, which is k plus 1, which is the case right after the case is true, we could say that, hey, this is good enough to prove that it works for all cases. Now, how come? Well, if we look back to step 1, we checked the first case and we showed that, hey, it works here. So if now all of a sudden I make k equals to 1, what do I know? The case after 1, which is 1 plus 1, which would be the second case, is true. And if the second case is true, we kind of start this infinite loop. Then we come and say, well, then we can now make k into 2, and if 2 is true, then k plus 1, which would be 2 plus 1, which would be the third case would be true. And you could see that this becomes an infinite cycle. We just keep going over and over. So if the first case is true, second is true. Well, if the second is true, also third is true. Well, if the third is true, fourth is true, and so on. Okay. Another example that a lot of people use to kind of connect to induction is like Dominos. So imagine if we have kind of like, you don't have to put this in your notes. Imagine if we have equally spaced dominoes, okay? And let's pretend that we have, I don't know, 1,000,000 of them. So what happens is, see, if I knock down the first one, that's kind of like the first case, right? We knock down the first one. Now the question is, if the first one knocks down the second one, can we then say the 1,000,000th one will be knocked down? And the answer is yes. How come? Because look, if these dominoes are equally spaced out, if the first one knocks down the second one will knock down the third one will knock down the fourth one. Even though we haven't seen it yet, we know that through inductive reasoning, these are going to knock each other out, and then eventually the 1,000,000th one is going to be knocked out as well. So that's kind of like what's going on here. See, the first one works, and then we showed the one after the first one also works. Okay, and then with that case, we kind of create this infinite loop. Now, you might be wondering, well, why do I care to make this second statement? Okay, this second statement is going to be very, very important. And here's the comment I want to make on this. So this comment about proof by induction, which for me, when I first saw it, I was like kind of thinking, wow, this is kind of weird. How am I going to, because there's going to be some uncertainty. How do I get rid of this uncertainty? And then it's kind of like, to me, it's like magical how it works. So, you know, it's really, really nice how things work out the way they do. But the idea here is that we will need to use the statement from step 2 to show step 3 is true. So what you'll notice is step 2 is going to be crucial because we're always pretty much going to be using it in step 3, which is our important step, to show that the case n equals k plus 1 is true. Okay, so with that said, we're going to do 3 examples, and hopefully that will be good enough for you to kind of be able to work on these problems on your own. As always, if you need you know, more clarification questions, don't hesitate to reach out to me and email me. Okay, so let's look at example 1. So we're going to say prove that for all natural numbers n, the sum of the series for n minus 2 equals to 2n squared. Okay, so what we're saying is we're trying to prove that the sum of the first n terms of the left side could be found by this equation. So for instance, here's what I'm saying. If I want to add the first 2 terms, like when n is 2, 2 plus 6 is 8, this equation is saying, hey, you don't need to just grab the first 2 terms and add them. You can just plug in 2 for n here, which notice what's 2 squared, which is 4, times 2, which is 8. So if I want the sum of the first 3 terms, which would be 2 plus 6, which is 8, plus 10 is 18, if I plug in 3 for n here, I get 3 squared, which is 9, times 2 is 18. So we're trying to show that, we're trying to prove that this is in fact true for all cases. And you could see why proof by induction works out perfect here. So here's what we're going to do. So by proof by induction, step 1 is what? We're checking just n equals 1. So we're showing that n equals 1 is true. So if n is 1, what does that mean? I take the first term on the left side. So the question is, does 2 equal to 2 times 1 squared. That's the question mark. What is it that I know? 1 squared is 1, which is times 2, which gives me 2 equals to 2. So notice how the first step is probably the easiest step because, and I mean the first couple steps are very straightforward. First steps, you're just checking in, hey, when my domain value, or when I use the first value, which in this case, if we're talking about natural numbers, the first number is n equals 1, how do does it work for that? Now, the second case is a statement. So we're going to basically say, assume that the case n equals k is true. What is it that we're saying? That is, if I take the first k terms here, so what am I doing here? Now I'm replacing n with k. So we're saying 2 plus 6 plus 10 plus all the way to 4 times k minus 2, that's going to equal to 2k squared. Okay, so we're assuming this statement is true. So we're saying, hey, whenever you go from 2 plus 6 plus 10 all the way to 4k minus 2, that's equal to 2k squared. Now, here's the weird part. See, when I first saw this, I was like, wait a minute, we have some uncertainty here, right? Because we don't know what k is. We don't know how far we go. So how am I going to use this? And more importantly, in step 3, see, here's what we're going to do. What is it that we want to show now? We want to show that the case n equals to k plus 1 is true. So we want to show this, okay? We haven't proven this, so we have to show this. So that is, we want to show what? Now, if I go back up to this top equation, what am I replacing n with? K plus 1, right? Because that's what n is. So we want to say that is 2 plus 6 plus 10 plus all the way to 4 times k plus 1 minus 2 is equal to 2 times k plus 1 squared. Now, if I show that this side and that side are the same thing, then I've proven it, right? Because I've shown this works for the case k plus 1. Okay, so with that said, we see once again, what's the weird part here? I'm saying, wait a minute, I have this dot, 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 this uncertainty. How could I get the left side to equal to a single expression? And right, and this is where kind of like the magic comes in that I always talk about. But here's the important part. See, if you compare this to the top equation, I replaced n with k plus 1, okay? But if I were to ask you, hey, how many terms does the left side have? You would say it has k plus 1 terms, which means if it has k plus 1 terms, what do you notice in step 2? We have how many terms? We have k terms. So if I compare this, the number of terms that this guy has to the number of terms that that guy has, this guy has one more because look, this has k terms, this has k plus 1. So in other words, and here's where the fun part comes in. So what am I going to do? I'm going to start off with the left side, and my goal is to make the left side look like the right side. Look, this statement is not true. I'm trying to show it's true. So that's a question mark. So what I'm going to say is, look, 2 plus 6 plus 10 plus all the way to 4 times k plus 1 minus 2. I need to show that this somehow becomes that. Okay? So with that said, if you notice, I could rewrite this and say, well, this is still the same thing as what? 2 plus 6 plus 10 plus all the way to 4 times k minus 2 plus 4 times k plus 1 minus 2. So I didn't change this up. All I really did is I said, look, if this is the k plus 1th term, what's the term right before the k plus 1 term? It's the kth term, right? So notice how the k plus 1 just this is the kth term, that's the k plus 1 term. So obviously this is going to be right before k plus 1. So first term, second term, third term, kth term, k plus 1 term. So why did I do that? Now here's where the beauty of it all comes in. Notice how all of this that I just boxed is the same thing as what we had in step 2. And what is it that I'm doing in step 2? I'm saying, hey, anytime you see 2 plus 6 plus 10 all the way to 4k minus 2, that's the same thing as 2k squared. Now look at the beauty of this. That uncertainty is now gone, because what could I do? I could say, look, this guy I know equals to 2k squared. So I could say, look, this guy equals to, so this is going to be 2k squared, plus now I have also the 4 times k plus 1 minus 2. 4 times k plus 1 minus 2. Now, I'm not done yet, because what do I need to do? I need to simplify this and get this to become 2 times k plus 1 quantity squared. So let's continue this on the other side. So what is it? Is 2k squared. So if I go to the other side, because I'm running out of space, so if I have 2, and what was it? It was 2k squared plus 4 times k plus 1 minus 2. Let's simplify now. What is this equal to? 2k squared plus, if I distribute the 4, I get 4k plus 4 minus 2. And then if I combine like terms, I get 2k squared plus 4k plus 2. And then what do you notice here? And look, the good news is I kind of know what my end result's going to be, right? So because we know what we want it to turn into. So if I grab this, what could I factor out? I could factor out a 2. And if I factor out a 2, I have k squared plus 2k plus 1. And what do you notice? This guy factors, which is going to be 2 times k plus 1 squared. And if you notice, that's what I wanted to show, right? So what did I just show? I just proved, if I go back to the start of this, I just started with this guy, which was the k plus 1 term, and I worked its way and I showed that it's true. It ends up equaling to the same thing as that guy, which that was the requirement for step 3. So once we prove this, the proof is complete. So we showed that that statement is true. Okay? So let's look at one more example. And for example 2, you might want to pause this and then try to do it on your own and then play it and see how your answer compares to mine. So we'd say prove that for all natural numbers n, we have the following. We have 3 plus 6 plus 9 plus 12 all the way to 3n. That sum is equivalent to what? 3n times n plus 1 over 2. Okay? So you should try to pause this and try to do it on your own and then press play. But with that said, so let's go to step 1. We're checking check n equals 1. So if I'm checking n equals 1, what do I know? The first term is 3. And then if I replace this with 1, I should also, and that should be equal. It shouldn't be plus, it should be equal. The question is, does it equal to 3 times 1 times 1 plus 1 over 2? Question mark. And what do we notice? 3 equals to, what happens to the top? 3 times 1 is 3, times 2 is 6 over 2, which implies 3 equals to 3. So that checks out. Okay? Now, step 2, if you remember, it was just a statement. So we're going to say, suppose n equals k is true. So that is, we're going to say this going all the way to k, so 3 plus 6 plus 9 plus all the way to 3k, that's the same thing as 3k times k plus 1 over 2. Now what is it that we want to do? The third step, so remember this statement is true, which means I'm going to use it in the third step to help me out. So we want to show that n equals k plus 1 is true. So what is it that we want to show? That is, we want to show 3 plus 6 plus 9 plus all the way to 3 times, now instead of n, I'm going to replace it with what? K plus 1. K plus 1. That's going to be the same thing as what now? Now, if you remember our original equation, I'm going to replace n's with k plus 1's. So that's going to be what? It'll be 3 times k plus 1. And then if I replace this n with the k plus 1, it'll be what? K plus 1 plus 1, which would be k plus 2 all over 2. And that's a question mark, right? The question is, does this equal to that? So once again, if I start off with the left side, and my goal is to show that it looks like the right side. So that's the same thing as what? 3 plus 6 plus 9 all the way to 3 times k plus 1. And once again, this has k plus 1 terms. So the term right before the last term is the kth term. So that'll be 3 plus 6 plus 9 plus all the way to 3k plus 3 times k plus 1. And now why did I do that? Because from step 2, what do I know? All of this is the same thing as 3k times k plus 1 over 2. So this is the same thing as 3k times k plus 1 over 2. So if I replace that, that becomes 3k times k plus 1 all over 2 plus 3 times k plus 1. So now what I want to do is I want to simplify this, combine them, and hopefully this will turn into that. And once it does, then we're basically done with the proof, because we're showing that this guy is the same thing as that, right? That's the idea, right? This question mark means, hey, start with one side, which we always start with this side, show that it equals to that. So what do I get now? If I distribute, actually I don't need to distribute this k plus 1, I don't think I need to. Let's get a common denominator first. So I would have to multiply top and bottom by 2. So what do I get? I get 3k times k plus 1 plus 6 times k plus 1 all over 2. So the reason why I didn't distribute is because what do I notice? Both of these have a k plus 1, and if I look at my end result, I also need a k plus 1. So what do I need? I could factor out a 3 from these guys and a k plus 1. So if you distribute it, then you'd have to factor again. So I kind of see a shortcut, and I'm saying to myself, hey, don't distribute because these guys have a k plus 1, and I need a k plus 1 anyway, so I'll just leave it as is and I'll factor out. So notice how both of these have a 3. So I'm going to factor out a 3, and I'm also going to factor out a k plus 1. Now the question is, what am I left with inside here? Well, from this, if I take away a 3, that's gone. If I take away the k plus 1, I'm just left with a k, and then plus. From this, if I factor out a 3, I'm left with a 2. And if I factor out the k plus 1, then that's gone. So I'm just left with a 2 all over 2. How nice is that? Notice how I just got straight into that. So that completes my proof. Okay, so I want to do one more example, which is going to be slightly different than what we've seen, but this actually has its own nice results as well. So we're going to say here, use mathematical induction to prove for n is greater than or equal to 3, that 2n is less than 2 to the power of n. So now look, my conditions are what? When n is a natural number greater than or equal to 3. So my first case would be what? When n is 3, right? So remember, in the other ones I started with n equals 1 because we had no restrictions. Our restriction was what? The natural numbers, which means the first natural number is 1. Now here we're saying the first natural number we want to start with is 3. So we're going to check n equals 3. And if n equals to 3, what do I get? I get 2 times 3 is less than 2 to the power of 3, question mark, right? Which then what do I notice? 2 times 3 is 6, is less than 2 cubed is 8, which sure enough that is. Now the second part is just a statement, right? So we're going to say suppose n equals k is true. That is, what is it that we know? 2 times k is less than 2 to the k. So we're making that assumption. Okay, so anytime we see 2k, we can say, hey, that's automatically less than 2 to the power of k. So now we want to show that n equals k plus 1 is true. And by the way, see, the reason why we're saying that this assumption is true, because we know there is one k value where this works, which is 3, right? So what's important is we want to show the one right after this is true. So that is, we want to show that 2 times k plus 1 is less than 2 to the power of k plus 1. So this is kind of the important part. So what is it that I'm going to do? We start with the left side, right? So we start with the left side. So I should put a question mark here because we don't know if that's true. So we're going to say 2 times k plus 1. So let's simplify. We know that this is equal to what? 2k plus 1. And look at what the beautiful part here is. I see a 2k here, and what do I know about 2k? 2k is less than 2 to the power of k. So 2k plus 1 is going to be what? Less than 2 to the power of k plus 1. Hopefully you guys see this, right? The plus 1 is not the problem, right? Because look, obviously if 2k is less than 2 to the power of k, then 2k plus 1 will be less than 2 to the power of k plus 1, because that plus 1 is sticking around. It's the same thing. Okay, now here's where things get a little tricky, right? Because what is it that I want to do here? I want to try to get this to be that. Okay, so here's where it gets a little tricky. Well, look, 2 to the k plus 1, what do I know about 1? 1 is clearly what? Less than 2 to the k, right? That's a fact. Because, and what do I know? How come? Because we know since k is greater than or equal to 3, right? You could make the argument that, hey, 1 is not always less than 2 to the k, because what if k is like, let's say, a negative number, like if it's negative 1, so it'll be 1 less than 1/2. That makes no sense. But since our restrictions are saying what? The smallest k could be is 3, we know this is true. Now, why is that important? And you'll see, hopefully you'll see why now. We could then say 2 to the k plus 1 is also less than what? 2 to the k plus 2 to the k, right? That's true. So if, because this 2 to the k and those 2 to the k are the same, but we know that 1 is less than 2 to the k, so 2 to the k plus 2 to the k is less than 2 to the k plus 1. Now, why do I like this? Because these guys are now, they have the same base and the same exponent. So what could I do? I could add these. So how many 2 to the k's do I have here? 1. How many 2 to the k's do I have here? 1. Right? So think of it this way. If we were to say, look, let me kind of make more sense of this. If x is equal to 2 to the k, then what is it that we know? X plus x will equal to what? 2x, which, what's x, by the way? It's 2 to the k. So this is the same thing as 2 times 2 to the k, right? Because you see that, we know that, hey, in math, it's by now you guys are experts with this. X plus x is obviously 2x, which if x is 2 to the k, then 2x becomes 2 times 2 to the k. So what I'm trying to get at here is what? 2 to the k plus 2 to the k means we have how many 2 to the k's? We have 2 to the k's. Now, here's the other beauty of this. Now, notice how these have the same bases. And what is it that we know? Anytime we multiply the same bases, we add their exponents, which, what's 2 times 2 to the 1 times 2 to the k? It'll be 2 to the k plus 1. Notice now what is it that we just showed here? We just showed that 2 times k plus 1 is less than 2 to the k plus 1, which is what we are trying to show here. So all of this that I did, this implies 2 times k plus 1 is less than 2 to the power of k plus 1, which is what we want to show, and that proves our statement. So just keep in mind that this was a little more tricky because I somehow had to get introduced 2 to the k plus 1, which was from this step from here to here, right? So this one was not as straightforward as the first two examples. It took a little more thought to do. So, and remember, these the proofs by induction, some of them won't be as straightforward, and sometimes you're going to have to sit there and think about what's the correct approach to take with this, okay? So, you know, play around with the problems from the homework. This is actually a very, very interesting and important concept of mathematics also. It will show up over and over and over as you go on to higher levels of mathematics. So it's your first time seeing it. It'll take some time for you to kind of get the hang of it, but just be patient with it, and I promise you you'll get better with this with more and more experience. So it's very important that you put your time in the homework and work on these problems. Okay, so that takes care of this section.